A very good day to all. I'm here to present my individual assignment for Control System Fundamental subject. So before I start my presentation, let me introduce myself first. My name is Yushmita Anak Perempuan Timugilan. My matric card number is B0821100150 and I'm from class 2 BEEI and my section group is 1/2. So I will be presenting a question from session 2020 and 2021 and I will be presenting about question 2 in section B. So let's start the video. As the start of my presentation, first I would like to explain about my first question, which is question 2A. Question 2A is about a robot that used to move 55-pound bags of salt pellets. As you may see, there is a figure B2.1 shows a vacuum robot lifts 2 bags of salt. So in Roman 1, the question is about, so identify what type of response is produced and it needed a justification as well. As we could see from the question, they have given 4 types of response for second order system, which is overdamped, underdamped, undamped and critically damped. So what will happen when the step input is injected to the system? So that's how we are going to determine what kind of response it will produce, and it needed a justification as well. Continued by the Roman 2 question, where in Roman 2 they have given the assumption of K and we have to estimate the 4 parameters of the transient response. And followed by question Roman 3, a unity feedback is connected to the system as shown in figure B2.2. So in that case, we have to determine the range of gain K to ensure the stability of the system. So that was the part for question 2A. Now moving on to question B, which is a figure B2.3 is given with the feedback control. So as the first Roman of the question, we have to find the static error constant when the step input, ramp input and parabolic input is given to the system with a different time interval. So that's for question Roman 1. And question Roman 2 is we have to determine the system based on question Roman 1. So in order to get Roman 2's answer correctly, we have to answer Roman 1 correctly. Question Roman 3 is still the same, where we refer to the same figure, which is figure B2.3. It is where we calculate the steady state error of the system when it is injected with a value of Rs equals to 50 TU bracket T. So once we're done calculating, we have to justify whether it is a good system or not. So that is the last part of the question. Let's take a look at the solution of question 2A Roman 1. As requested for the question, we have to identify the type of response produced. So as we can see, by taking second order system, the characteristics equations is s squared plus 4s plus 10 is equals to 0 is compared with the characteristics equation which is stated over there. So we can compare the value of Wn equals to square root 10, and we also can find out the damping factor is actually less than 1. If the damping factor is less than 1, the system response is called underdamped type. In question Roman 2, they have given the assumption of K is equals to 1 and we have to estimate the 4 parameters of transient response. The 4 parameters are maximum overshoot, peak time, settling time and rise time. Where all these parameters, they have their own formulas and we have to substitute the values from the previous equation given and from the characteristics equation as well. So we can see the maximum overshoot percentage have been found and the peak time have been found as 1.02 seconds and the settling time is 2 seconds, where the rise time is 1.166 seconds. Not to forget the MP, which is the maximum overshoot, is 7.715% and the working have been shown clearly in the slide. Okay, in Roman 3, they have required to find the range of gain K to ensure the stability. In order to find the stability of the system, we have to use the Rouse table to find what is the range of k for the stable system. So as you see in Roman 3, I have stated the formula of unity feedback system is s power of 3 plus 14s squared plus 50s plus 100s plus k is equals to 0. So beside there is a table used as route table. By solving this route table, we can find the range of k to ensure a stable system, where it has been solved and the range of k is equals to -10, less than k, less than 600 is to ensure a stable system, where we could find the range of k for a stable system. Okay, let's move on to solution question 2b. In question 2b, Roman 1, we have to find the static error with the feedback control system given in figure B2.3, where the feedback control system is 5 over s power of 3 plus 3s squared plus 7s plus 15. In order to find the static error constant when input is stepped, the s value will be replaced with 0, so we can find the value of kp, which is 1 over 3. And after that, we have to find the steady state error, which is so called as ESS, with the formula of 1 over kp. So once we implement the formula, we can get the constant value, which is equals to 3. Moving on to the next error, which is static error constant when input is jumped, where in this time kv is equals to limit s to 0, where we will times the numerator and denominator with the value of s. So once we replace the value of s is equals to 0, once we solve it, we can get the value of kv is equals to 0. In order to find the steady state error, which is ESS, is the same formula implemented, which is 1 over kv, and we can find out the value is infinity. Previously in static error constant, when input is stepped, we do not times numerator and denominator with the value of s, but in static error constant, when input is jumped, we will times the numerator and denominator with s. So followed by the third static error constant when input is parabolic, which is ka is equals to limit s to 0, and this time we are going to times the numerator with s squared. So once we could solve as the previous two static errors, we can get the value of ka is equals to 0, and the value of steady state error, which is the ESS, follows the same method, which is 1 over kv, and we can find out the value is infinity. So the last but not least, the steady static error due to rs is equals to 50 tu bracket t. So at this part, we can find the steady state error, which is 1 over kv as well, same as the previous one, and we can find out it is also infinity. As we manage to solve Roman 1, in Roman 2 we have to determine what type of control system it is. As we can find out from the static error constant values, it is a zero type system. In order to determine what type of system it is, we have to know the static error constant values. In previously Roman 1, we have find the static error constant, which is kp, kv and ka's value. So from there we can determine it is a system 0 type. How do we determine is that if a type 0 gives an error with a step input and infinite error with a ramp or parabolic input. If it's type 1, the system gives no error with step input, a constant error with ramp and infinite error with a parabolic input. And there is also another type, which is called as type 2, where the system has 0 error with the step or ramp input but an error with parabolic input. So as we compare with all this, we can know that type 0 is our type where it gives an error with a step input and an infinite error with a ramp or a parabolic input. So in Roman 3, we have to justify whether is it a good system or not. As we can find out from the static error constant, where it is not a good system because whatever it is replaced with the steady state error, it will always equals to infinity, where there will be no constant value and there will be no values at all. So that shows it is not a very good system. So that is all from me. I hope this video is understandable and also useful. So in order to get the full PDF of the solution, you can find it in the description box. And thank you so much for the time.